So now that we've seen how oxidation of NADH through the electron transport chain produces ATP, let's look quickly at a few shuttle systems that are required to shuttle cytosolic NADH into the mitochondria. So here we have our glycolytic pathway, and we'll talk about this in a couple weeks. What I want to draw your attention to is this step here, where we produce NADH in the cytosol. So there's 2 NADH produced for the oxidation of each glucose molecule, and this NADH needs to be transported into the mitochondria to be used to make ATP. We have 2 options for shuttling NADH or its reducing equivalents across the mitochondrial membrane, and the first and the most common of the shuttle systems is the glycerol 3-phosphate shuttle. So if we look here on the cytosolic side, what you'll notice is our pool of NADH is here, and we'll transfer electrons from NADH to dihydroxyacetone phosphate to generate glycerol 3-phosphate and NAD+. So in this reaction, NADH is oxidized to NAD+, and dihydroxyacetone phosphate is reduced to generate glycerol 3-phosphate. The glycerol 3-phosphate can then be transferred into the mitochondria through the outer mitochondrial membrane. And once inside the mitochondria, the reverse reaction occurs where glycerol 3-phosphate is then oxidized to dihydroxyacetone phosphate, and the electrons are transferred to FAD in the inner mitochondrial membrane. This leaves us with FADH2, which is now inside the mitochondria and can be used in oxidative phosphorylation. The resulting product, dihydroxyacetone phosphate, can be shuttled back out of the mitochondria and into the cytosol. So in this case, what you should take note of is that NADH itself does not cross through the mitochondrial membrane, and this will be consistent. What passes through the mitochondrial membrane is a compound that carries these electrons in a reduced form, and for the glycerol 3-phosphate shuttle, this carrier is glycerol 3-phosphate. Once inside the mitochondria, glycerol 3-phosphate is oxidized, and those electrons are transferred, in this case, to FAD. The other shuttle we'll talk about is the malate aspartate shuttle. And this shuttle has several roles in metabolic processes, and for right now we'll focus primarily on the transfer of cytosolic NADH into the mitochondria. In this case, cytosolic NADH is used to reduce cytosolic oxaloacetate. The enzyme here, malate dehydrogenase, facilitates this reaction, and the resulting products are malate and NAD+. From here, the malate can be shuttled into the mitochondria, and in this shuttle system, the malate will be our carrier of electrons. Within the mitochondria, the reverse reaction is catalyzed again by malate dehydrogenase, where malate is oxidized to oxaloacetate, and the electrons are transferred from malate to NAD+ to generate NADH. What you'll notice also about this shuttle system is that the resulting oxaloacetate can take part in a transamination reaction, and we'll talk more specifically about transamination reactions. But briefly, transamination reactions involve the transfer of a nitrogen group from an amino acid to a keto acid, in this case the keto acid oxaloacetate, to produce an amino acid, aspartate, and the resulting keto acid, alpha-ketoglutarate. This will allow us to shuttle both alpha-ketoglutarate out of the mitochondria and aspartate out of the mitochondria. So the important take-homes from this shuttle system is here we can use the conversion of oxaloacetate to malate to shuttle cytosolic NADH into the mitochondria. And once in the mitochondria, if metabolic needs are such that we need carbon in the cytosol, we can shuttle the remaining oxaloacetate out of the mitochondria again, either in the form of aspartate or alpha-ketoglutarate. So sometimes I'm asked by students, what is the clinical relevance of all of this? And with these shuttle systems, sometimes it's difficult to understand what the purpose of shuttling things back and forth across the mitochondrial membrane is. From my standpoint, this impacts metabolic processes, but from a clinical significance standpoint, there's also clinically relevant implications. So first of all, there's a clinically relevant and clinically used inhibitor of the malate aspartate shuttle. That is amino oxaloacetate. This directly inhibits the malate aspartate shuttle. And there's a significant amount of literature that looks at what the consequences of inhibition of the malate aspartate shuttle are in different scenarios. So here are a few papers that may be of interest to look at what happens if we inhibit the malate aspartate shuttle. The first is targeting of glutamine metabolism in breast cancer using our malate aspartate shuttle inhibitor. The second is the use of the malate aspartate inhibitor in mitochondrial infarction. And finally, the use of this inhibitor, it has been looked at in changing of energy metabolism of microglial cells. Look at these papers and see how this changes metabolism in either in breast cancer cells, in cardiomyocytes, or in microglia. These would be good topics for the discussion board pathway posts.